Hello, my name is Dr. Benjamin Prather, and today I'm going to talk to you a little bit about um, a video series that I've been watching online and enjoying online about something called the mechanical universe. And let me introduce myself. So this is me, and I will be talking today, and I've put together a bit of a PDF file to go through and talk about the mechanical universe. And so first, this basically is just my notes and thoughts. And the Mechanical Universe is a series of videos in collaboration between James Ellias and Chantel Roth, who go by Inductica and Red Pill 6313 on YouTube. I'll also be, so the essence of their theory is to base the model of the universe on continuum mechanics. And so I think it'd be useful to introduce the actual formal language and theory of continuum mechanics. And Bob McKinty has a nice online book that is free and available, and I have the link right here that you can see. And it has all of the mathematical descriptions of a classical elastic media. And I also have some inspiration in here from Richard B. Hill's marathon videos on gauge theory and Higgs mechanisms and superconductivity. I'll provide links to those in the descriptions. And but let's go ahead and get into it. Well, before I get into their video, I do want to talk a little bit about, I feel like if we're presenting a review of something, we should come with our own biases. So everybody has biases. I've got biases coming into this review, so I figured I'd outline that. So first, in standard string theory, recently, I say that, it's like 15, 20 years ago, 30, 40 years ago, maybe even by now, 1D strings have been generalized to 2D membranes. And the idea is each particle represents either a vibrating resonance of a string or the end of one of these strings. But why stop at 2D? Why not go one more? Why not go to a three-dimensional membrane? And at that point, why do we even need more than one membrane? Instead, what if particles are just isolated solitons in this one three-brane that makes up the universe? And so that's my mental model for what a ether is. It's just a three-brane, three-dimensional manifold that all of dynamics is playing out in. And quantum mechanics could emerge as waves in such an ether, and general relativity could emerge as the motion of that ether. At least, I think that's the part of the dream that I share with the video authors. Also, several of the comments in the video discussed, what role would velocity or temperature have? And both velocity and temperature are related to emergent phenomena coming from the fact that in a classical media, we're dealing with things that are made up of molecules, and the continuous model fails at the molecular level. And these are the energies that are going back and forth between the molecular level and the classical continuous model. This suggests that an ether, at the most fundamental level, should not have viscous terms or temperature terms, because if we're dealing with the most fundamental level, there shouldn't be a more fundamental level for energy to leak out to. However, I do want to hedge my bets on whether another layer exists. In the video, the Continuum Mechanics video that I plan to post a link to this video in the comments of, at 510, it talks about, all different scales and how you got the Planck scale. But I suggest that, even at the length of the Higgs scales, perhaps that's where the standard model fermions are emerging, similar to how supercharges emerge in a superconductor. So my main point about that is gauge theories produce massless particles, and the standard model fermions have mass. So that suggests to me that they are not the most fundamental particles. Cooper pairs of superconductors acquire mass through the Higgs mechanism. So maybe the standard model particles are Cooper pairs of a more fundamental massless particle. And further, perhaps these massless particles are what give this three-dimensional manifold its dynamics. And so that could be even related to the nature of the ether itself. I invite you to watch Richard B. Hill's video, Superconductivity in the Higgs Field, or at least parts of it. It's a marathon of a video. It's like 4.5 hours long for how one might be led to think this might work. Also, I mentioned that the particles are expected to be solitons in this field, and that has consequences. For example, topological solitons are actually boundary conditions of differential equations. So perhaps we're dealing with the boundaries of the manifold. So maybe there's a local handle, and then when you put that into 3D, it would look like you would see the two necks around closed spheres, and then that would produce two particles, a particle and an antiparticle. And perhaps it's those boundaries that are the fundamental particles. These are sketches of ideas that I've had, but those are some of the biases that I bring to the table to this discussion. So first, before going on to the mechanical universe idea, my ideas on the mechanical universe itself, I want to review continuum mechanics, because the mathematics of continuous media is not a new subject. Cauchy, Green, and others, Stokes, Young, come to mind, developed the theory nearly 200 years ago. And advances in material science has produced physical examples for many of the edge cases. So many of the things that were like, when they were first doing it, is this even possible? We now have physical material science models that exhibit a lot of exotic behaviors that 200 years ago you couldn't have even imagined a physical material doing. Bob McGinty's book, online book, Continuum Mechanics, provides an excellent summary of the math and a nice notation that I want to follow here. And a large motivation for this is the video would have been helped by using the notation consistent with the standard notation of continuum mechanics. So here are I will say that that site is based largely on the elastic properties of a nearly incompressible solid, specifically rubber, because I suspect that Bob McGinty was perhaps a tire engineer before retiring and deciding to write a book. But regardless, he uses capital X to represent the reference coordinates, usually the position at some initial time. Then little x represents the position of the material as a function of time. So then u is a displacement vector. That is how much each position moved relative to where it started. And then we can define our velocity vector to be the derivative of the displacement vector. Most classical media have a density, and then the momentum of the particle is just a momentum, and actually technically has a momentum density, is just a momentum is just the density times the velocity. And further, we can take angular momentum is just the density times the displacement cross the velocity. So that is the classical angular momentum tensor. I will note that the mechanical universe introduces a spin tensor, which is just the angular momentum without the density. So if we had a uniform density, those two would be proportional to each other by the density of the ether. Finally, we have the deformation tensor F, which is a second-rank tensor that tells us how to get from a differential element in the initial coordinate to the differential element in the deformed coordinates. And using the deformation tensor alone, we can define the strain tensor. And this measures how much stretching and twisting is going on at each element in terms of a matrix, so you can keep track of all the principal directions of that stress and strain. And finally, we have a 4 tensor. It has 81 terms, but we will see that a lot of those turn out to be 0 or repeats of each other. So it has 81 terms because it's a 3 by 3 by 3 by 3. It's a classical 4 tensor. So it's 3 spatial terms, 4 dimensions is 81 terms. And the stress tensor and the elasticity tensor, this elasticity tensor is like the Hooke's law constant that relates the strain, the stretch, how much the material is deformed, to how much forces and stress each particle, the ether, then feels and is exerted on it. That needs to be balanced or cause an acceleration. So this elasticity tensor tells me how the strain relates to forces. So now we're getting into the video, and I timestamped it here. At 17:08 in the video, there was some discussion of, are we talking about a pressure or a density? And using this language that we have here, the stress tensor represents a restoring force in the medium. The diagonal terms are the principal stresses. For a fluid, these are all equal, and then the pressure is just 1/3 of the trace, which would just be the components if they are equal. But that generalizes to even if they're not equal. If we have strains in different directions, the pressure would still be the average of those. The off-diagonal terms correspond to shear stresses, how much shear is in the media. And for a fluid, that's forced to be 0. That's kind of the defining property of a fluid. The density is just a determinant of the strain tensor. Well, it's proportional to it. The elasticity tensor describes how transformations produce stresses. Thus, this tensor describes how pressure and densities are related, even for a non-isotropic media. That's why it needs to be a tensor, is because the media may not even be isotropic. It may have different stresses in different directions at this level of generality. So hopefully at that talk at 17:08, that kind of gives some language to help clarify the difference between pressure or density and how they're related, and how these tensors help give a language to help bring those together. All right, shear pressure. So at the 1 hour and 6 minute and 55 second mark, there's discussion of shear pressure. And with a bachelor's in mechanical engineering, the term shear pressure, it should have been called shear strain, because pressure is when it's along a principal axis. When it's shear, we call that a strain. So if we just take the vocabulary of classical elasticity tensor, we can use that metaphor to discuss the mechanical universe. So it's not a shear pressure, it's a shear strain. This is also a good time to mention that because the strain tensor and the stress tensor are symmetric, this tensor is forced to have only 21 independent parameters. And if we further assume that the ether is isotropic, that's going to reduce to 2. And these are the bulk modulus, which describes how much the volume will change with the pressure, a uniform pressure. And the shear modulus describes how much resistance there is to shear. And again, it's the shear modulus that goes to 0 for a fluid. The mechanical universe talk very often, one of the beautiful videos in that that they embed into the video is a model of spin flow, where you got all the things rotating around. I found a model of that where there is actually, when you calculate the shear strain using that definition above, the shear strain goes to 0 everywhere. So there is a model of that spin flow where you have the center rotating around continuously, and the outside static, that has no shear anywhere. So that means the bulk motion of that flow pattern is the accumulation of local infinitesimal rotations alone. So there is no stretching or shearing. It's all just local rotations that the accumulation of those small rotational changes produce the entire motion. So I found that flow to be interesting. Now, Hooke's law versus viscosity. So now I'm looking at the 3:30 mark in the video. And here, the elasticity tensor is basically the constant in Hooke's law. And we're talking about it in 3D instead of 1D that Hooke's law was looking at. The restoring force density, because it's proportional to, well, it's the force per mass per volume. Well, so the force would be acting on the density, the density of the ether. So it's a force density, not a force. It's a force per volume. But it's proportional to the displacement gradient. Viscosity produces a force resisting the velocity gradient, not the displacement gradient. If we were to take this analogy to a one-dimensional linear model, elasticity then would be the spring constant, while viscosity would be the linear damping. I should note that in a Newtonian fluid, viscosity is actually quadratic and not linear. Okay, and also in continuum mechanics, rheology looks at materials that have both properties. So if we have both elasticity and some viscosity, how do these properties play together to make the material properties that we behave? Plastics have a stronger elastic properties, so they're more like a solid that flows a little bit sometimes. And non-Newtonian fluids have stronger viscous properties, so they are fluids that have some memory of their current configuration and some restoring force, but the viscous properties dominate the elastic properties. And for both of these, one defining characteristic when you have both of these is that you have hysteresis, where over deformation, over a loading cycle where you put on a load and bring on the load, it doesn't go back to where it starts, but there's a net deformation that even comes in a metal. If you get past the yield stress, it will deform when you get past the yield limit, when you get into non-elastic motion of metals. In the mechanical universe model, they're using a purely elastic solid with no viscosity. And at the fundamental level, I believe that that is the better model because there is no more fundamental level to be producing the liquid or viscous effects. So I agree with the mechanical universe on that viewpoint. So now we're going to look much more specifically at the mechanical universe model. So the aim of the mechanical universe is to derive Maxwell's equation as an emergent phenomenon from the motion and properties of an elastic solid. Now, the nature of Maxwell's equations are that if we can identify what the scalar potential and the vector potential are, everything else just stems from that. So once we get those two down, all of Maxwell's equations will fall into place. We don't have to worry about how electromagnetism fits in once we have properly defined phi and A. The mechanical universe very clearly defines spin to be the displacement cross the velocity, which is, I would argue it might be better used angular momentum, but it's angular momentum divided by the mass density of the ether. It's unclear what the intended scalar potential is. It's loosely described as a density, but a density of what? Densities are often described as divergences of vectors, or the accumulation of divergences of vectors. Is it the velocity divergence in velocity? The divergence in velocity? Is it the divergence in displacement? Is it the divergence in spin? I put those in order of apparent likelihood, so I believe that's what they were talking about, but it may be these in decreasing order of confidence. It was not precisely stated to where I saw it. May have been, I may have missed it. But I was not quite sure what the phi was supposed to be a density of. Whatever phi is, the electric charge is just the Laplacian of whatever phi is. And this is roughly the amount phi varies relative to its surrounding neighborhood. And for this to be electromagnetism, the fundamental particles have to kind of look like a Dirac delta function at that point. All right, E is very clearly stated to be the curl of the spin. So they mentioned that prior models that they had considered used pressure instead of spin in a fluid model. And if we use pressure, it's tempting to define phi to be the pressure and A to be the gradient of pressure. However, that would produce the electromagnetic field being zero as a vector identity. And that's related to the fact that when you try to build a model on that, then it's going to be non-trivial to polarize, to produce polarized waves when you're trying to generate the electric 4 potential from the time derivative and gradient of a scalar function. Conversely, Maxwell equations alone mean that if we have any scalar function f, the field, whatever phi we define, minus the partial of f with respect to t, and a plus the gradient of that scalar function, yields an electric and magnetic field that's exactly the same as the one we started with. So using P for F suggests that pressure waves in an ether are invisible to the mechanical universe model. So if whatever ether is, if they're pressure waves, then the mechanical universe model is not going to pick those up because that would be a scalar wave. So not only would the magnetic potential be zero for such a wave, for a pressure wave, but the electric potential would be zero, and a pressure wave would not impact in the ether, would not impact the electromagnetism of the mechanical universe. And indeed, that leaves pressure waves available to model gravity, which was mentioned in a previous video. So I like that seems to be working well for the mechanical universe model. At 4.1, there's discussion as to which gauge is this model in. And it's a vector identity that the divergence of the gradient of a vector field is zero for any vector field. There's nothing special about spin here. It could have been any vector field. Thus, this definition of A in the mechanical universe model must be using a Coulomb gauge where the gradient of A has to be zero. I will note that angular momentum, so the spin is basically the angular momentum up to a constant of the density of the ether. And the angular momentum, one of the things about angular momentum is if you set the origin at different places, you're going to get a different value for the angular momentum, but the changes in angular momentum are the same everywhere. So it's almost like angular momentum itself is a gauged theory to where the gauge depends on the coordinates. So if we set different big x's, perhaps we define u based off of different time frames using different times as our starting points, we'll get different u vectors. That's going to produce a different angular momentum, and that could represent the nature of what this gauge freedom actually looks like. So the gauge freedom phi could represent a freedom of such a choice. Indeed, as we saw above, a longitudinal scalar wave could very well be like the invariant that gauge condition is representing. So in the actual mechanical universe model, there could be a physical, actual longitudinal scalar wave going on that the gauge condition of the electromagnetic field potential makes go away, that then would then reappear when we look at the gravity of the situation. Since S is actually an axial vector, because the cross product of two vectors produces an axial vector, I'm fond of the idea that phi could represent a pseudoscalar. And since we're dealing with angular momentum, it very much seems like the helicity could be a very good choice. That's a side tangent that perhaps I should work out in the future. I'd like to see how that could work out or if that works out. All right, at the 30-minute and 15-second mark, you highlighted a paragraph from a paper that had a bunch of seemingly abstract mathematical nonsense that you were not clear why that was obvious, but it seemed to fit with your theory. I wanted to kind of disentangle what was actually being said on that paper, why it's obvious. However, well, we'll get to that part in a minute. So the quoted statement is simply observing that the spin group is a double cover of the rotation group in every dimension, in particular 3 dimensions. And the angular momentum is the preserved Noether current for the rotational symmetry of space-time. So that's going to cause that ratio of 2 factor between the angular momentum vector, which is the Noether current for the rotational symmetries, and the spin representation, which is in the double cover. Your model helps to visualize the non-trivial mechanical picture of what this trivial mathematical result is telling us. So the mathematical result is trivial, but the consequences of that are not. So the picture of the spinning sphere helps give us a very concrete physical picture of that non-trivial mechanical picture that results from this trivial mathematical statement. All right. So mostly I like the mechanical universe. Otherwise, I wouldn't have spent this much time looking at it. But I do think there are going to be some obstacles that the theory is going to run into and are going to have. One of them is not that it's going to exhibit quantum mechanics, the wave behavior, because it's going to have electromagnetism. The waves are inherent in the theory. So the wave behavior is not going to be an issue. And if we manage to work out what the solitons are, those will create the discrete particle-like entities. But one issue in classical mechanics with solitons that could be here is, why are they going to have fixed sizes? Because solitons have an amplitude, that the wave shape of the soliton is going to depend on the amplitude, but there is a continuous distribution of solitons usually. So why are these going to have fixed sizes? These could be related to homotopy groups, but that was an aside I went on while drafting this together that I don't have any more thoughts beyond that. But with that idea that solitons, like water waves in a channel, the soliton depends on the size of the disturbance, the shape of it. So why will they have fixed sizes? And that would mean for the model, the similar consequence would be, why don't electrons have a continuum of charges? So why do electrons have a specific charge instead of there being a sea of electrons, each with their own charge? So that is the biggest obstacle that I look forward to seeing how that is addressed. And with that, I hope to see more of the mechanical universe as it gets developed further into the future. And thank you for your time. And if you enjoyed this, leave a like, subscribe, and thank you for your time.